Hi, and welcome to this Dev Summit 2022 Masterclass on SOAFEE-based software-defined vehicle development for autonomous driving. The Masterclass is a continuation of the workshop ARM and AWS created for Dev Summit in 2021. The creation of this Masterclass is a collaboration between SOAFEE, Autoware Foundation, and eSync Alliance. Let me start by presenting today's speakers. Today we have Stefano Marsani from AWS, who is a worldwide tech leader for autonomous driving. Christian John, who's the president at Tier 4 North America, and also chair of the Strategic Planning Committee at Autoware Foundation. Mark Singer from Excelfore, who runs product marketing, and he's also the chair of the marketing work group at eSync Alliance. And myself, Casper Ornstein-Mecklenburg from ARM, and I'm a performance analysis engineer. With no further ado, I'll hand over to Stefano.
Okay, so hi everybody. Nice being here, Stefano Marzani from AWS. And let's review the agenda for today's session. So first of all, I'll give you an introduction of what does cloud native in automotive means. And then we'll see how SOAFEE started, right, thinking about how to implement and bring this to market, and eWorld, that is the first reference implementation of SOAFEE, and Casper will go through that. And then why we selected Autoware as a first workload to be deployed on top of this novel way to build software in the cloud. And Christian will talk about it. And then finally, a very nice piece that is how we can do and how that changes traditional operations, the automotive sector, like over-the-air updates, OTA. And Mark from Excelfore will give us a look about that. But let's get started. I'd like to first of all, introduce you our what we do in AWS and what as AWS we present to our customer when we talk about automotive development. So our automotive development infinity workflow. This is the base, right? It's what we told our customer for the past 2-3 years. So you see all the customer equipment on the left. It can be developer desktop with some evaluation kit on their desks, hardware in the loop rigs, test fleets, production fleet. All the system exchange data with the cloud that is represented by the infinite diagram on the right side of the slide. You see we have that ingestion, and then customers typically do process this data, create metadata, organize this data through databases, and this becomes a very important construct for them. It's the automotive data lake, right? With the automotive data lake, all the data is there, raw, well organized, indexed, searchable, and this is serving the whole organization. And the whole organization have different usage for it. For some of customers like Mobileye or Here Maps, they develop HD maps or do labeling activities for machine learning, deep neural network training. Some customers do hardcore automotive, like powertrain development in terms of algorithm to optimize the performance or the profile of a particular control algorithm for the specific engine. And then two very automotive bases that are simulation V&V that plugs this infinite circle on top of the V model for the automotive sector. Software is done, we deploy it, and it's infinite because everything restarts again. Data comes in and the process will continue. In the last 2 years, we really thought in a strong partnership with ARM that we can do a little bit better, right? And achieve further steps and optimization in this whole infinity workflow. Introducing the concept of parity. We really asked ourselves, what does it mean to improve the developer experience in an age where we have consolidation of the electronic architecture, where we have scarcity of hardware, right, in terms of evaluation kit or other equipment to develop, and how we can make CI/CD loops in general more performant, better, and better democratized. And we said we need for the cloud to work in parity with the embedded environment that we can find in our left side of the diagram, in the evaluation kit, in the cars, in hardware in the loop rigs. For this bottom part, the software needs to be executed with the same level of parity that we find inside the ECU, with the same exact environment. And what does parity means? Parity means different things. So we have instruction set parity. So for example, in cloud, we have our Graviton instances that are based on an ARM, it's an ARM-based microprocessor, a Nuverse N1 based. And so we have instruction set parity with all the ECUs out there that share the same instruction set. So ARM64, what does it mean? It has a deep implication because, for example, for the first time, we can lift in cloud real-time operating systems or systems, OSs that are typically used in electronic control units. We can run them in the cloud. And then we can extend it a little bit more. So, for example, to the CPU architecture parity, think about specific ARM cores like Cortex-A, Cortex-M, right? So this is not just the instruction set, there's a little bit more functionality. And here we have the possibility to run the instructions natively with ARM, for example, and emulate the components of the specific functionality that makes the CPU unique in terms of characteristics. And here we even have a marketplace offering with ARM, the ARM virtual hardware that implements exactly that. And then SoC parity. So we extend even more beyond the CPU, and we start to integrate specific components that can be emulated, integrated, simulated on top of in cloud, and then to arrive to a system parity that somebody calls the digital twin. So, and all of this, it's not just a theory. Again, last year at the summit, more or less 1 year ago, we implemented the first demo where, as you can see in this slide, we took the Autoware .auto YOLO object detector. Imagine the developer building, making a code modification, going through the code pipeline in cloud already in AWS cloud and generating an ARM64 container out of it. And then look at the stack on the right. This is not just running on top of Linux 2 or Ubuntu, so typical server side, server operating system, but on Yocto. On Yocto Linux, this is an embedded operating system. So the stack is in parity with what happens in the embedded devices from the operating system up. And then you see in the same stack, Yocto Linux, EWL, the first reference implementation of SOAFEE, and Casper will discuss about that in 10 seconds. And on top of it, our workload under development. When we are done with the testing in the cloud, we just take that and execute it in the embedded edge with absolutely no modifications at all. And this already been demonstrated, and many exciting things happened after this Dev Summit, and I can't wait for Casper to give you these updates. So Casper, to you.
Thanks, Stefano. Scalable Open Architecture for Embedded Edge, abbreviated SOAFEE, is an industry initiative which was launched just over a year ago. One of the main goals with SOAFEE is to extend the cloud-native software experience to the automotive industry. This is an important part of moving the industry towards a software-defined future. SOAFEE proposes a software architecture making use of cloud-native technologies for automotive software development and deployment, and with time meet the strict requirements inherent for automotive, such as functional safety and hard real-time. SOAFEE provides the ecosystem with an open-source reference software implementation. This enables users to make modifications suited for their needs and create prototype solutions to try out new concepts. Next, I'll share more about the SOAFEE architecture and reference implementation. Here we can see a simplified view of the high-level architecture of SOAFEE. Starting from the top, we have the domain-specific application. In this context, domain-specific refers to some software which performs a certain task. The applications are deployed using containers. The applications run on top of SOAFEE reference implementation. The requirement for reference implementation is that it enables the features which the SOAFEE architecture dictates. Using standards-based firmware creates alignment and allows a user to easily get an operating system up and running on any type of hardware which follows the firmware standard. An example of this is ARM's System Ready program, which is a compliance certification program based on a set of hardware and firmware standards. By enabling SOAFEE's vision of decoupling hardware and software, a lot of possibilities arise. Using the cloud gives us availability and scalability. One use of virtual hardware is to enable a user to deploy software on hardware that is not available or does not yet exist in silicon. I hope this gives you a high-level understanding of the SOAFEE architecture, and next, I'll talk about how we actually use this architecture for this project in more detail. Starting from the top, once again, we have Autoware, which is the containerized autonomous drive application, which is developed by the Autoware Foundation. eSync over the air, which is the containerized updating service, which is developed by eSync Alliance. eWall is the SOAFEE Linux reference implementation. It's a custom Linux distribution. Using standards-based firmware allows us to run eWall in the cloud and at the edge. In the cloud, AWS Graviton instance is running eWall. And finally, at the edge, we use the Ava developer platform developed by AD-Link. Next, let's dive deeper into eWall. Edge Workload Abstraction and Orchestration Layer, abbreviated eWall, is the SOAFEE Linux reference implementation. Okay, so what does this mean? eWall has features which enable the way SOAFEE envisions how software should be deployed, that is, in a containerized and virtualized way. Let's take a look at some of the pieces which make up eWall. Docker is a container engine used to run containers. K3s is a lightweight Kubernetes distribution for container orchestration. Xen is a Type 1 hypervisor for hardware virtualization. eWall is a custom Linux distribution built using the Octo project and is provided through the open source repository Meta eWall. It can be built in two different ways. Bare metal, meaning that eWall runs directly on the hardware and application workloads are run in containers. Virtualization, meaning that we can deploy virtual machines which run the application workloads in containers. These containerized application workloads are not part of eWall. You bring your own container. One of the benefits of the Octo project is its layer model development methodology, which is key to customization. And this enables users to take eWall and modifying it to suit their needs. In this project, we deployed eWall in the cloud on an AWS Graviton instance and at the edge on an Ava developer platform. This gives us runtime parity in the cloud and at the edge. This is thanks to the Octo project and that hardware vendors agree on and implement standards-based firmware. We use the bare metal and SDK version of eWall, making it easy to deploy in the cloud and at the edge. And SDK gives us tooling, allowing us to compile out-of-tree device drivers as needed. With this, we have a consistent runtime environment, enabling us to run the same container without any recompilation necessary in the cloud and at the edge. We can see here on the right that AWS has three different versions of Graviton. C6G, which has the Neoverse N1 core, G5G, which also has the Neoverse N1 core, and is also GPU enabled with an NVIDIA Tesla T4. And C7G, which has the Neoverse V1 core, which has a larger vector engine, making it more computationally powerful, for example, for machine learning workloads. AD-Link's Ava developer platform has a chip from Ampere with the Neoverse N1 core. It's like a desktop developer machine with PCIe slots for acceleration. It's great for prototyping. Now I'll hand over to Christian, who will talk about the autonomous drive application workload, Autoware.
Thanks, Casper. Hi, everyone. I'm Christian John, CJ, as many of you know me, and I'm going to give you an overview of Autoware, which is one of the first workloads that's been adopted as a blueprint for the SOAFEE framework. Autoware is a complete application for autonomous driving built on top of ROS 2. Autoware is independent of vehicle type. It's been adopted into all form factors of vehicles with different sensor suites. It's governed by the Autoware Foundation and completely open sourced under the Apache 2.0 licensing framework. There's some useful links here from the Autoware Foundation where you'll find documentation, including architecture specifications, start guides, tools that are useful for working with Autoware and so forth. And of course, the Autoware open source software. Now, I mentioned independent of vehicle type. Here you see some representative vehicles that we've integrated Autoware into. It's been deployed throughout the world, North America, Europe, throughout Asia. Passenger vehicles, large form factor buses, small form factor shuttles, cargo last mile delivery solutions. Autoware was even used as the reference software in the Indy Autonomous Challenge. The first lap ever run around Indy Motor Speedway was run by Autoware. So very adaptable, different vehicle form factors, sensor suites, very flexible software. Now, we're going to talk a lot about software-defined vehicle development today, and OpenADKit is the initiative that was started by the Autoware Foundation, working closely with partners like SOAFEE, eSync, and MIH to bring software-defined vehicle development based on Autoware to market. So what we're doing here is we're taking Autoware, we're integrating it into the SOAFEE framework as far as a containerized workload, and then integrating other services such as eSync over-the-air framework, and then working with partners like MIH, which are defining open specifications for next-generation electric vehicle platforms about how to bring in these types of autonomous driving applications into their framework. And Autoware OpenADKit with SOAFEE and eSync is a key component of that MIH platform that we're working on. Now, where is OpenADKit today? So we've implemented the first releases of the OpenADKit that takes Autoware, containerizes it, and implements it on top of the eWall framework. We've also integrated as a service the OTA eSync capability, which is then used to update functionality in the Autoware container. And all of this now is running both in the cloud and on the edge. We have a Graviton EC2 instance for an ARM processor where we're running this stack in the cloud. And then on an AVA development platform, on an actual edge hardware platform, we can demonstrate the exact same capability. And as Stefano talked about, we've achieved ISA level parity. The ultimate goal, of course, is that we get to system level parity. But right now we're demonstrating the ISA level parity in this current configuration. Now, where we want to go ultimately with the OpenADKit is to enable a true microservices architecture and start to integrate additional service capabilities on top of a heterogeneous compute architecture. And this is where implementing a digital twin of the underlying hardware architecture comprised of GPU, CPU, acceleration logic, high safety MCUs running the eWall framework, and including things like hypervisor, hardware abstraction layers, and then the Autoware application in a microservices architecture would break up the functionality of perception, planning, control, localization, and so forth into separate containers on top of this framework. So this is the goal of the Autoware Foundation, to work with SOAFEE and our partners to enable this type of an architecture. Now, the other key component that we talk about is the cloud native piece. And really what we're talking about here is developing the tools and the framework to take this OpenADKit, integrate it into a vehicle. And as you see here, upload data from the vehicle, get that into the cloud, as Stefano talked about, the data lake, where we're going to store all of the sensor data collected from the vehicle. We're going to annotate that data. We're going to create scenario data for different types of situations that a vehicle will be operating in. All of that goes into the simulation platform that can either be run in the cloud, so using the Graviton EC2 instances to simulate the framework in the cloud, running it on a test bench, so hardware in the loop type simulation, and then using OTA to push updates that are validated into the cloud into the vehicle, and then do further testing, refinement, collect more data, and start that whole process again. So one of the key components of this whole framework, of course, is the integration of the OTA. And now I'd like to hand it over to Mark, and he's going to talk a little bit more about eSync and virtual vehicles and how that fits into this framework. Thanks.
Thank you, CJ. I'm Mark Singer from Excelfore. I'm also chair of one of the working groups of the eSync Alliance. an automotive trade association focused on standardizing the data pipeline for OTA updates and diagnostic data. The front of the eSync Alliance, the face of the eSync Alliance, are the tier 1 suppliers of the automotive industry, although we also have automaker and semiconductor company members as well. And in fact, we are open to and welcome any participant in the automotive ecosystem. eSync is a standard specification for a bidirectional data pipeline comprised of a server, a client, and agents. And the specifications for eSync define the pipeline architecture, the behavior, the features, the behavioral specification at each level, and the APIs and protocols for correspondence. Through this, we build a compliance interoperability spec so that servers, clients, and agents can come from different sources and work together. And existing servers or in-vehicle OTA masters or edge devices can be brought into compliance with the eSync specifications to participate in the pipeline. On the right here, you see the basics of what takes place at each level of the pipeline. Typically a server in the cloud speaking to one client in the vehicle, the client managing the cloud interface, and then also managing a network of agents. The agents are distributed throughout the vehicle, and you have agents for the edge devices. They are not necessarily resident in the edge devices, but it is through the distributed agent construct that we get the scalability and flexibility of the eSync pipeline. With eSync, we can create a single pipeline for both OTA updates and data gathering. It's a structured approach, as you see, for rapid implementation and for high reusability. It scales to any number of ECUs or sensors in the vehicle. We have now 7 different automakers deploying vehicles with eSync, some 14.5 million vehicles in those programs. And we have vehicles with as few as 1 device and vehicles with as many as 65 devices or more being updated by eSync. It scales well to diversity and works equally well with domain master architectures, with gateway-based architectures, and with zonal control architectures. It's highly flexible. Part of the flexibility comes through policy-based OTA. Policy is a construct within eSync that allows you to set the parameters by which this pipeline will operate. And without recoding the pipeline, set different parameters, perhaps in different geographies, because you may find different regulatory environments. If you want to be shipping vehicles into the EU versus into North America versus into China, you may find differing policies and regulations as to how OTA will need to function. With eSync, you don't need to recode your OTA pipeline, simply set the policies. You get the highest levels of data integrity for OTA to ensure the payload at the end is correct. You get full logs for traceability and compliance, and you get best-in-class cybersecurity. This is a diagram you've seen earlier in the presentation. The undertaking here amongst the Autoware Foundation, the eSync Alliance, SOAFEE SIG, and Amazon Web Services has been to create a scenario where cloud and edge can achieve the highest degrees of parity. Part of that parity is in the software update management, and that's what eSync is providing. So we have integrated eSync with the Open AD kit from the Autoware Foundation, integrated and tested to know that this is going to work well. And eSync then becomes the OTA distribution for your workload containers to both the virtual and the actual platforms. So you have one software update management system for both the cloud environment and the physical environment. So how is that achieved? We have an eSync client and an agent constructed for the workloads. The agent is delivered in a Docker container. The workload agent is provided as source with a Yocto Linux recipe on GitHub. And with this combination, you then get advanced OTA features in the Autoware OpenAD kit. You get all of the cybersecurity, you get all of the policy constructs, safe vehicle assurance, etc., with a fully developed OTA pipeline, even in your distribution platform for the OpenAD kit. So you get a working account on the eSync server, that account on AWS. This is sponsored by the Autoware Foundation with the OpenAD kit, but you can then transfer this to your own AWS account in time. You get OTA campaign management. You get to secure the upload of your payloads. You get to select the targets for your payloads, select the policies for the campaign, select the time frame for the deployment of the campaign, and then you can deploy. When you deploy, you get secure correspondence and delivery of your payloads, full integrity for the installation, and full logging and reporting for traceability purposes. This is the construction of the learn by run environment, as was mentioned earlier in the presentation, where you now have one deployment mechanism for your cloud native Gravitons, your Workbench AVA kits, and your actual vehicles. You can use the same software update management system for all three. Together, these allow us to run and manage virtual vehicles in the cloud and at the edge. So you have AWS Graviton EC2 providing accessibility and scalability. You have EWAL providing the runtime parity between the cloud and the actual devices on the edge. You have Autoware providing the containerized vehicle software. And you have eSync providing the deployment of the containers. You select the content that you want to ship, and then you choose the targets. And these can be actual vehicles. These can be Workbench AVA platforms. And these can be Graviton cloud platforms. And the eSync server will take care of the distribution for you and provide you full logging and traceability.
Thanks, Mark. This brings us to the end of the masterclass on SOAFEE-based software-defined vehicle development for autonomous driving. A huge thanks to all the speakers who presented today, and to the developers who have worked hard to make these technologies merge. For more information on SOAFEE, Autoware Foundation, and eSync Alliance, and last year's workshop, find links in the description. Thank you for tuning in. Bye-bye.